Now in this video we're going to focus on migratory insertion, and now this particular reaction step is crucial, connecting both the oxidative addition, which is what we talked about on series of our videos right there, and a specific video which is of recently reductive elimination. Now migratory insertion is the bridge between both the beginning and the end of a cyclic catalytic reactions that occurs in mainly organometallics, and this is actually crucial for building strong, rigid and identifying specific compounds in various chemistry reaction manufacturing industries. Now the focus of this particular reaction comes in two steps. Now the two steps first begins with where a ligand, like for example X, is cleaved from the metal, which we'll call M, and now migrates. This is really important. That is the first step to another ligand, which is Y, that is currently bonded to the same metal, which is M. Now the big important factor here is that both ligands X and Y, they must be cis to each other in terms of the configuration relative to the metal. Now the next point we need to take note of is that in terms of the insertion, this is when we notice that our Y ligand is actually between the metal, which is M, and our ligand, which is X. So visually speaking, you should see that kind of observation on that particular catalytic structure. Now this particular formation of this particular structure after the first step is driven by the addition of an extra neutral ligand, which we'll call Ln, where it could be a phosphine, where we have Pb3 with the ligand having our lone pair right there that's actually donated to the metal, or we have a particular carbon monoxide which actually inserts itself as well to the metal, so it could come in that particular form, or various solvents. Now this actually leads to the formation of a coordinatively saturated complex in that particular reaction step, and that will be crucial for the stability of that particular structure, the integrity of the overall catalytic structure that is building more of those compounds. And then once that is done, that could lead to the final step, which is elimination. Now looking at the skeletal mechanism for these two steps in here, first we have our metal, which we have right here, and this metal initially bonding with X and Y. What we notice now is that going to the next step, what happens is that the X will migrate to the Y, and what we notice is that we have our M having just one bond to the Y, and Y is bonded to X. So what happens next? What is happening is that our complex is coordinatively unsaturated. So in order for we to saturate this particular complex, we introduce a ligand which has a lone pair, and that lone pair is actually donated to the metal. And what happens as a result is that we have our product that is formed out of this particular migratory insertion right there. So we can see the insertion happening right there, and we can see the migratory step right there. So let's look at a couple of case scenarios. The first case scenario occurs in a Wilkinson catalyst, where we have the hydrogenation of an alkene. Now this is the alkene right there, and what you notice is that we have a Wilkinson catalyst which already is hydrogenated already at the oxidative addition step. So we have two hydrogens that are actually cis each other, and what happens is that we perform our first step, which is the partial bond formed here as a result of the metal coordinating with the pi system of our alkene, and what you notice is that one hydrogen is missing. The hydrogen kind of slightly shifts away of tangent from this particular introduction of the alkene. Now the reason for that is to be able to introduce our hydrogen, and to accomplish that, what happens is that this pi system donates this electron to this particular metal center, and then this hydrogen is then inserted into this particular carbon right there. So as a result, what that leads is the formation of our chain where we have our hydrogen right there, and over there we have our R group. So the last step is where we actually eliminate our product from this particular process, and to do that, we have the second hydrogen right there. This particular bond right here cleaves and then picks up this hydrogen, and this hydrogen bond here is cleaved and it's donated back to the metal. So what you notice here is that the metal complex results in the chloride moving back there to its position, and then we have our product, which is an alkane with the R group position right there. So what we see is the hydrogenation process occurring in the alkene, forming alkane from a Wilkinson catalyst, which is what we have initially right here. So that is about it for the first case, and the second case involves the building of organic ligand chains, which is in the form of a Ziegler-Natta polymerization before the elimination step. Now the big condition here is that the group of interest, which is the ligand, must be unsaturated, being either this here or alkene or alkyne right there. So let's start off with the mechanism. So for the first one, which is a carbonylation, we have this R group here bonding with this carbon, therefore causing it to leave this metal, and as a result to perform a coordinatively saturated complex. This ligand is then introduced to this metal, and what results in is the ligand increasing by 1, and the metal is actually bonded to the carbonyl, and this carbonyl actually has the R group formed right there. So this is applicable to carbometallation or hydrometallation. In this case, we'll focus on the carbometallation. We have our R group bonded right there, and what happens next is that we have this particular ligand completing the saturation, and what happens is that we have an increase in the ligand right there with the metal, and we have our long chain with the R group right there. So in here we're going from an alkene to an alkane right there, and finally here we have our alkyne with a triple bond right there, and this triple bond, what happens is the R group inserts itself right there, or migrates, sorry, there, and there we have our ligand, which causes the insertion, and what results in is the ligand increasing by 1, and we have the metal attached to this carbon that is doubly bonded to the other carbon, and on this other side we have our R group. So we're going from alkyne to an alkene right there. So that's about it for this particular reactions here. Hope you're able to understand the migratory insertion, where we're migrating first before inserting into a bond that is between a metal and a ligand, which is facilitated by a neutral new ligand inserting itself to form an coordinatively saturated complex. So all the same, stay smart, believe in yourselves.